Hi, I'm Kusunok, cloud storage engineer at NTT Communications. NTT Communications is a Japanese telecom tier 1 ISP, and we are providing also data center and public cloud. For our public cloud or internal app, I've evaluated many storage products. So today, this is user story. I'd like to talk storage performance evaluation in our environment and capacity planning for our telecom cloud. So our performance evaluation itself is kind of simple. Perhaps you already know it, but to sustain reliable cloud as a carrier cloud provider, I'll give you what kind of requirement, limitation we've considered on the performance evaluation. And using the results, I'll present our capacity planning example and to show what restricts our service, our business in some case other than performance or capacity. So this is today's agenda. Firstly, I'd like to explain our public IaaS and required storage function and storage evaluation and capacity planning. So first of all, I'll explain NTT Group. So this is kind of boring, sorry, but we have so many NTT Group companies. So please let me show our business position in the group. So NTT Group consists of Japan regional company and mobile communication company and application manager service. And here is our position. This is so in NTT Group, our business is global ICT solution, network and data center hosting and cloud. And this is our cloud service. Our cloud service brand name is Enterprise Cloud. Our cloud, Enterprise Cloud, provide public IaaS here and PaaS based on Cloud Foundry, bare metal, and with hypervisor, VMware. This is based on OpenStack and NFV Matter. And also we are providing software-defined network. So this SDN connect to bare metal and virtual machine and storage. And of course, customer application will be deployed on this IaaS infrastructure, and various customer application will use our storage through this IaaS infrastructure. It's over SDN. So that is quite overview. And let's see more about our SDN storage network. We provide two planes. So one is data plane. That is used for everything. Communication among virtual machine and bare metal, and internet access, other data center, AWS connectivity for hybrid cloud. So this data plane is used for everything. It means this plane is not so stable. Many traffic may come here. For example, DDoS attack might come here. So we prepare one more plane. We are smart. So storage plane, it's stable because only bare metal is connected to this storage plane. And this plane is separated physically. It's independent. So storage plane is really stable. And for this plane, we use software-defined network technology. Underlay is VXLAN. And the customer VXLAN traffic will be encapsulated, decapsulated on the top of rack switch. So storage itself don't need to be deal with such VXLAN packet, but technology is based on VLAN. So, and this is our storage service lineup. The storage service, we offer block service and file storage service. For block, customer want reliable performance, so we provide a provisioned IOPS block service, 2 IOPS per gigabyte and 4 IOPS gigabyte. And for file, customer want low-cost storage, so we provide also best effort NFS. And now I showed our cloud infrastructure and our storage service briefly. So work is over. Our job is just deploying server, network, storage. That's all? Of course not. Customer want to use reliable, predictable performance. They expect telecom grade. So one of our challenge is how we provide provisioned storage in shared cloud. In our cloud, can customer use guaranteed storage performance at any time, any situation? Simple answer is no. Server could be dedicated. Yeah, server is relatively inexpensive. So, and storage, we can provision storage performance in advance. So storage, it's okay. But network is really difficult. Network cannot be dedicated. And as you know, network line and the device is really expensive. So on our complicated VXLAN network, it's difficult to control customer mixed traffic with QoS. It could be, but it's really high cost for our SDN controller. We need more development resource to achieve this. So currently, at this moment, we will not guarantee the end-to-end storage performance. So just provisioned storage service. And here is the graph. So bare metal is dedicated and the storage is provisioned, but network plane is shared, basically shared and best effort. And also virtual machine share their hypervisor network interface card. So furthermore, customer use their application on favorite OS. How can we expect customer workload? Asking customer? No way. We provision just typical IOPS storage, 2 IOPS gigabyte or 4 IOPS gigabyte as storage flavor, so that customer could use those flavor on demand based on their use case or their business. So to provide such provisioned performance for each customer, we need multi-tenancy function. First, it uses tenant isolation. Of course, customer A should not see customer B's tenant traffic data. So minimum requirement is just chat of authentication. But the best is invisible. And another important multi-tenancy is for network. As I stated provision previous slide, we use VXLAN. But on VXLAN, our customer can use any VLAN and any private IP address. So customer A can be used 192.168.1.1 on VLAN 100, and customer B can use this famous private IP on another VLAN. So storage should have to deal with such kind of duplicated IP on another VLAN. So to achieve such requirements, probably storage needs some network multi-tenancy and VLAN tagging support. And another requirement is performance QoS of course, to provision the storage performance. Cap IOPS and throughput is enough for us, but nice to have is minimum performance, burst mode. It can be more advanced storage menu, and the option is dedupe count-wise. Some storage can distinguish deduped storage capacity tenant-wide or storage array-wide, whole cluster-wide. Of course, whole cluster-wide is better. And I asked some storage vendor guy to develop such multi-tenancy function and QoS. But every time their question is, why only storage I have to deal with such complicated matter other than storage? Network layer should process this. But we cannot. Another solution, storage gateway. It's storage expose simple storage function to this gateway, and the gateway manage multi-tenancy, VRF and QS, but to achieve it, heavy gateway is needed. So development is really high cost, and routing control on our SDN, it's also high cost. Our SDN controller have to deal with such kind of complicated storage QoS on mixed storage packet. It's huge. So I showed our requirement for multi-tenancy and why we need it for provision performance storage service. So now I'd like to present our storage evaluation considering it under these requirements. So this is our testing environment. Basically, it's almost the same as our production, but it's just an example. So our scale-up type storage have two controllers and connected to disk shelves, and this storage controller is connected to storage leaf switch through 10G links. And this storage leaf switch is connected to spine switch, the 40 gigabit link. It's totally redundant. The link aggregation is using. And server side, same. Bare metal server have two 10G link and also EX server testing appliance. And this is scale-out type storage testing environment. It's almost same. Yeah. Instead of scale-up type storage, here is scale-out. And storage configuration, almost same as production. RAID, disk group, disk share, volume, VLAN IP, interface on the array node. And the available capacity should be worst case in our evaluation. Example, 20% or 10%, because generally flash array need some free space for garbage collection. So on the network example, as I said before, we need network multi-tenancy. So on storage performance evaluation, we emulate such kind of multiple VLAN and I duplicated IP on storage layer and host layer. So all virtual machine could be used, same IP, private IP address. And workload client. Basically, we use general Linux, Ubuntu, or CentOS on bare metal ESXi. And several virtual machines have different IP VLAN, and open source benchmark software is basically VD Bench and FIO. That's basically VD Bench. And also we use testing appliance, load dynamics by virtual instrument. This appliance can generate iterative, reductive workloads with various parameters, asynchronous number, queue depth, NFS meta operation rate, and so on. So with open source tool, we can do same kind of evaluation, but such a few thousand workload is really difficult to gather the resource from many virtual machine and process, display. So that's why we use load dynamics for such kind of iterative evaluation. And workload definition. As I showed at previous slide, public IaaS is not enterprise. Customer use any favorite OS and configuration and application on our bare metal and virtual machine by themselves. Basically, we cannot touch it, see it. On network layer, perhaps we might be able to see it, but it's huge and mixed storage packet. So it's really difficult. And also any investigation for production could impact could impact customers' experience. So we are carefully for customer. So it's quite difficult to investigate real workload. So it's impossible to define customer real workload on public cloud. Okay. Then another question is this. Is there any typical workload on IaaS infrastructure? On IaaS, we use specific hypervisor software like VMware, OpenStack. So in some cases, instead of customers themselves, our managed VMware could mount Iskaji target. So our assumption is VMware might migrate or deal with storage access in good way on same data store. For example, two virtual machines write 8 kilobyte block to each VMDK file on same data store. In this case, if VMware software is really intelligent software, VMware data store can be deal with such kind of 8 kilobyte block aggregated to 16 kilobytes, have at NFS. So I tested it using load dynamics. So 2 VM in here, 2 VM read 32 kilobyte block, but aggregated request size on array is just 32 kilobyte. So we cannot see any aggregated packet on storage side. So there's no typical workload on IaaS. So we cannot expect any type workload, I think. So if customer wanna use database workload will come here. And if customer wanna use some office application or video application, so in this case, such kind of human workload will come here. So we cannot expect the workload. So our evaluation, we are using our just service description. Our service description is block size is 16 kilobytes and random access 100%. Read write is 80% to 20%. So it's almost software AWS, it's same. So it's a simple service description. We show such kind of service description in our website as provisioned IOPS. So we evaluate max performance with this defined workload. And also we test 50-50% read write and 100% case and 0% case. Because it's ideal workload, but some in our experience, some storage the performance become worse in these read write rate. So just in case we evaluate these read write rate. And also we evaluate the storage short and long evaluation time. So this is example on long time test, BAT effect. So after 10 minutes, we tested with 64 kilobyte block size and 64 clients. These clients have 64 VLAN and another IP address. So under such massive workload, some storage became worst performance after 10 minutes. So by previous slide, I explained our evaluation, network, storage configuration, workload. Now, I'm going to show we test storage with not only normal case, but also failure case. Someday, storage must have some failure, of course. So we should care to provide reliable performance to customer. So, and supported failure is basically one component failure. One hard disk or one network interface card must be failed. So, but over two failure dependency, over two failure, for example, two switch down or two controller down, it depends on service SLA. So, example, hard disk is really fragile, but two hard disk down should be assumed, but two storage controller down is not so. It's there. So I'd like to explain one failure pattern, basically. So for scale-up type storage, we assume one controller failure, sudden down or manual takeover for the management, firmware upgrade or something like that, and SAS card cable failure, so on one controller, and we will not support the loss of whole disk shelf. Basically, we assume storage disk shelf itself is robust. Storage disk shelf is just a bunch of hard disk. Of course, hard disk is fragile, but the disk shelf is have redundant power. So other component is just cable and box. And the scale-out type storage pattern is node down, and suddenly node down, and manual node down. And we not assume also SATA card failure. It's almost the same as total outage of node. So it's simple. And the common case in scale-up and scale-out is disk failure, and network interface card point failure, and single leaf switch failure over the node. So on previous slide, I showed the failure pattern. We assume these failure cause performance degradation, of course. First degradation pattern is momentary outage. Controller node failure during takeover and switch fail during path changeover. It could cause momentary outage over whole service. So customer cannot see any volume or customer cannot access volume. So it should be avoided. But such kind of controller failover time or switch path failover time is really limited. So if outage time is just momentary, for example, 10 seconds or 30 seconds, it's under the Linux default timeout value. So it could be okay. And second is short time failure. So during short time, some performance degradation could be caused. Control node failure during takeover, and RAID rebuild impact, and garbage collection flash array. So customer probably see some performance degradation to some extent, but the time is relatively short, probably a couple of hours. So it's based on service policy, but it could be okay. And this is a controller failure performance degradation example. Some storage product has 4 controllers. One node failure is supposed to cause quad performance degradation, but we see normal case 180K IOPS. But after the one node down, we see just 80K. So it's almost half. So some controller cause additional performance down. So third degradation pattern is, of course, a long time failure. Controller node failure after takeover during recovering process. Basically, recovering process take long time, or storage operator say another storage controller takes time to swap or something. So it could be a couple of day or a week is long time. So the RAID rebuild impact, if every day we see for failed SSD or hard disk, RAID rebuild is every day long time failure. So on previous part, I show our storage evaluation way and assumption for failure pattern. Now I show our capacity planning example using evaluation result. So how we decide storage capacity and the performance for customer? It's based on the service performance. Service policy. There are three policies. The first, customer is bountiful cloud native guy. So customer perhaps say some degradation is okay. So in that case, we don't need to care about any performance degradation. So only normal case is okay for that. Next policy is customer is not so merciful. Long time is not acceptable. So in that case, we should care long time failure performance degradation. So in that case, long time failure path. And the third one, finally, customer is cruel. Any performance degradation is not acceptable, like banker or some strong businessman. So in that case, short time performance degradation result would be used. So from now, considering capacity planning based on this policy, there are some factors that could limit the planning other than performance. So even if the storage system has great performance, for example, one storage array have 100 kilo IOPS and 10 terabyte per throughput. So if the storage system has great performance, these items could be limit our planning. So maximum volume number per array, or maximum account container number per system, or maximum QoS configuration number per cluster, or logical network interface number, or we need VRF and VLAN tagging support. So some storage have limited number of VLAN tag support. So from now, I'd like to explain how such kind of limitation number restrict our planning using this example. So first example is scale-up type example. Some storage array X. This array have low capacity, 10 terabyte, and usable capacity is 8 terabyte. Normally, we need some safe capacity. So, and from our storage evaluation, we see IOPS 16 kilo IOPS with normal case, and short failure is 20K, and long failure is 8K. So basically, our policy is long failure is not acceptable. Short failure is okay. So we choose 8K IOPS for evaluated performance result. And the calculation is this: 8K IOPS divide 8 terabyte. It's 1 IOPS per gigabyte. It's okay. So, but unfortunately, only 64 VLAN can be configured on this array per system. So it means 8 terabyte divided 64 VLAN equal 125 gigabyte per VLAN. So customers generally use at least one VLAN. So it means minimum customer's storage capacity is 125 gigabyte. It's much larger than 100 giga. Generally, public clouds offer minimum storage is 100 gigabyte. So it's not work. And so recent storage have great large SSD, 15 terabytes, 30 terabytes. Yeah, of course. We want to use such kind of big SSD. So such big SSD capacity explosion help to reduce rack space. Reducing rack space cause reducing power, reducing manpower, and so smaller rack space give us significantly lower cost. But above limitation prevent us to choose such large SSD. So considering gigabyte cost, really we want to use big SSD, but we can't due to such kind of limitation number. So another example is scale-out storage. Some scale-out storage cluster Y. This storage scale-out storage have node capacity is 10 terabyte, usable rate 8 terabyte, IOPS is 15K IOPS per node, and short failure performance is 40K per node. So considering the node itself, calculation is this: 40K IOPS divide 8 terabyte, 8,000 gigabyte, it equal 5 IOPS per gigabyte. It's better than scale up storage. But this product can have 512 accounts per cluster. So it means calculation is this: 6 node, 8 terabyte, double 6 divide 500 equal 93 gigabyte. It can be under 100. It's okay, but we cannot choose 7 node. 7 node is up over 100 gigabyte. So it means we cannot have more node in one cluster. But to consider the efficiency, redundancy, flexibility, manageability, of course, we want to have many nodes in one cluster. But these limitation number could be sailing. If just 6 nodes, is that truly scalable storage? Total capacity is almost same as scale up storage, traditional one. So summary. So we carrier cloud provider need multi-tenancy and QoS to storage, and using defined workload, our service description, we evaluate maximum storage performance with normal and failure case. And using this performance result, and using limitation number of the storage product, we are doing capacity planning. But such kind of hidden limitation number could restrict our business capacity planning strongly. So that is just user scenario, user story. So thank you for hearing, listening, and Q&A. Any question?
I have a few. So first of all, you mentioned this 100 gigabyte per tenant. About 100 gigabyte per tenant per customer. Is the average or a minimum?
Yeah, our minimum storage menu is from 100 gigabyte. Yeah, probably 100 gigabyte is okay for customer, we think.
So this is a typical application?
Yeah. Typically, minimum storage menu is 100 gigabyte. Yeah. Some customer perhaps we need 10 giga or 20 giga, but it's a balance.
And what is the scale of number of customers?
Number of customer for?
The amount of customers that get this chunks of 100 gigabyte each.
Sorry, I don't get
how many customers, kind of order of magnitude of customers that you may get with this 100 gigabyte chunks?
Oh, so one customer may use 100 gigabyte, but another customer can use another 100 gigabyte volume, right? So on same storage array. So basically, current our storage array is 21 terabyte. Yeah, it's scale out type storage. So customer can be 100. It's I think under 100 customer on per array. But normally customer buy more capacity. Yeah, 100 gigabyte is really small. So normally a couple of terabyte customer buy. So, but if every customer want to use 100 gigabyte, so in this case, the limitation number.
So you're planning for this 100 gigabyte scale, but you usually have customers that get more.
Yeah. But we have to expect the worst case.
Sure.
Yeah.
And your request for the multi-tenancy support.
Yeah.
So you need multi-tenancy
Yes.
in the data path. That's clear.
Yeah.
You need multi-tenancy on the management path?
Yes, also. We need multi-tenancy for management layer. So, sorry. Yeah, user tenant isolation. So, account or, system configuration, also another customer should not see that. So, management is also need multi-tenancy. Yeah. Is that all? Okay. So.
You presented a lot of interesting data.
Thank you.
Personally, what of this surprised you?
Surprise.
Yeah, what data did you end up collecting that was different than what you expected to see?
Expected to see the this. So yeah, this storage vendor say we have 4 nodes active. So even if one node down, performance is just for quad performance and for yeah, not so much. But actually, I did pulled out the node actually, but it goes down.
That's good though.
Yeah.
Is this data based on just one vendor or
Yeah, it's just one vendor example.
multi-vendor for that?
Another vendor normally scale up type storage have 2 controller. So in 2 controller, one node down, it means half performance degradation. So normally half performance degradation we see, but probably for node is yeah, it's interesting storage. Yeah. So, any other question? Okay.